Will be words. Well, Marco, any direct questions? Okay, as promised, I continue with some observations from 40 years of work in that domain, and also some, I guess, honest side remarks also about, maybe for the youngers, about smart moves we did and less smart things we did in that course. What I'm talking about is research, and I'm a professor, so research is done by the PhD students and postdocs, and I'm happy to at least give some advices or being involved in the discussions. And so, to be honest and fair, most of the work I'm talking about in the next few slides was done by Yannick Edinger, Dominik Schäfer and Martin Breitbach, but I feel at least being somewhat involved in the whole thing. And this goes back to my first sabbatical, actually, in 2010. I was visiting Steve Ward's group, and we were looking at the situation when, 2010, long ago, Amazon Web Services pretty much started hitting the road. Azure was on the horizon, so I think they released it earlier that year. And then there was the Google App Engine. And if you were looking at cloud computing at that time, you could find out that you either had small unit prices, but then you were less generic. If you were looking like a web application, so something that consumes HTTP requests, then the Google App Engine was actually a good hosting model for you, because you were charged by the number of requests that you were processing with your application. Or you were generic, but then with a rather high unit price. This was what Elastic Cloud Computing from Amazon was providing, and so you were charged by the hour. Got this one virtual machine, which was running for an hour. If you were finished in 45 minutes, there wasn't any spot market for the residual capacities at that time. Amazon was happy, and you just wasted it. And pretty much out of that idea, and looking at what my friend Justin did in his PhD thesis, we just thought about why not having something like an idle process running in your EC2 instance that is just taking some kind of, or offering the excess capacity to other providers there, and so kind of think about tit-for-tat sharing, whatever stuff, in order just to utilize what's around there anyway. So this was pretty much the idea at the start, and actually now that Guido is here, this also has some nice anecdote to a search interview or a talk I gave at Bamberg. So I was standing there and talking about things we did and then things we started to do, and I said, we don't have any idea what to do with it, but it looks just cool to do this. And it turns out that you can do things with that. So what we actually started to do or develop from that was, in various iterations, the Tasklet project, as we coined it. So today, you would say it's a serverless computing platform. So what we were offering or providing was a small virtual machine, the Tasklet virtual machine, that was running a bit like Niklaus Wirth's P-code from UCSD Pascal, or what he used in the earlier editions of his compiler literature. So it's a 2,000 lines of C code stack machine, so you can really deploy it easily anywhere where your C compiler compiles to. So we also provided to a number of platforms, with bachelor students doing evaluation and stuff over the time. Just a nice platform. We used a very restricted language, C++, so something which was pretty much statically typed, no dynamic data type, in order just to have a simple thing. And the core idea is to ship a Tasklet. And Tasklet is a closure. Closure means code and data in kind of one package, and you could deploy the Tasklet to any of the providers that would execute the Tasklet, and there will be something like a result provided if things are good. And one of the observations we did in the earlier times of the project was that you have different characteristics. So if your excess capacity is reached, your virtual machine is stopped, then there's no sense in reissuing a request if you don't get a result, right? So you have to find a new machine, deploy it there, and whatever. If your connectivity was just intermittent or disconnected because you you lost your 5G, 3G, Wi-Fi, whatever signal, then you wouldn't get a result, even though the result was correctly computed and available. You'll get it delivered once you get connectivity again, or you have to compensate by something like a local computation. So different situations, not errors, but different situations in these dynamic settings might require different kind of handling in order to cope with it. And this is actually the core idea that we had, that we said we have this task grid as kind of our abstraction for computing, similar to IP sending packets over the network. And if you want to have anything more than just hope for the best, so a best effort service, you have to do something like quality of computation on top of it, similar to transport layer in networking, where you then can start to tailor the different quality of services that you want to have, and that somehow abstracts from the underlying platform. And the core thing in the beginning, what we had was using this chunk abstraction, which looks a bit like inodes in the Unix file system, which was basically the inspiration for Justin's work. But we reworked on the whole thing over years and tried to make things a bit better from the abstraction. And this is pretty much now the kind of the later thing, how we ended up to starting with an abstraction for the quality of computation. If you feel reminded of something like your operating system's primer cost, yes, it's a separation of policies and mechanisms. So the idea is to find something on a higher level that we call goals that can be mapped to specific mechanisms. And obviously the mechanisms determine or can have different relations to what the goals do. So for instance, for reliability, you can either choose something which looks over history, be more reliable, so place it on a server, not on a notebook. You can use replication, whatever stuff. So on the right-hand side, the quality of computation mechanism is pretty much textbook knowledge. It's just pick your choices for the different settings. And here the hope was that we can somehow separate the concerns, and by that providing an interface that you can write the tasklets or configure the tasklets on higher level, independent from the concrete platform or the concrete settings, making it easier to cope with the dynamism in the whole system. And we pretty much focused on reliability, speed, and energy in the sense of offloading in the course of the project. And one example, for instance, for quality of communication is for speed using redundancy. So if you have redundant nodes or computation nodes available, you can somehow parallelize things. And smiling already, the Mandelbrot set is one of the most beautiful things you can use actually to show parallelism, because every single point of computation is independent from all the others, so you can really vastly utilize what's out there in parallelism, which is nice. And second, you can zoom in, it's fractal, so it's always beautiful and becoming even more beautiful the deeper you're diving there. So it's neat, and it's very simple to program. Anyway, so if you have the Mandelbrot set, which you can see here, then you can separate the whole thing, so divide it by 4, for instance, put them in tasklets, issue the tasklets for the computation. Oh, this is also one of the insights. If you're pursuing your career in academia and staying longer, don't use slides from my PhD students. I already started taking out animation from some of them, but it's horrible. And if you talk frequently, then it's something like, what's happening next over time? Anyway, first insight. Then you deploy it, and obviously once all the results are there, you can continue your computation. You have everything in there. Now, can we do any better? Well, if you have excess capacity, money is not an issue, or people are friendly, then you can just double the whole thing and deploy some. Did I say it? Never take. Okay, it starts here, deploys some more tasklets, and if they are collected and you have all of the 4 slices back, then you can continue. Obviously, for the cost of double spending, you can get some kind of a gain. So well, there's no free lunch. It's always balancing. So this obviously is a very simple, not amazingly complex mechanism, but you can hide it under the hood and use it as a nice abstraction. So the next thing that we were doing then is using a speed filter, which is also a rather simple thing. Like when your Linux boots, it performs a small benchmark computing the so-called micro-jiffies. So small amounts of time in order to get an idea how powerful your platform is. In a similar way, every time you're starting a task at virtual machine, so the container just performs a small benchmark just to see whether it's hosted on a powerful computer or a less powerful computer, and this is somehow tagged with no, it's not shown here. So the speed filter would be, all right, here are the tags now, where you can see the turtle indicating the obviously less capable and rather faster machine. And what we have seen before is if you have parallelism and you're waiting for one result and have just this one slow machine, everybody has to wait for that one slow machine. So obviously, just setting some kind of a threshold and excluding the slower machines should benefit, and surprisingly, it does. So if you're restricting this to just the two faster machines, you get a better speed of then including all the nodes. Again, textbook knowledge. So the mechanisms themselves are typically quite simplistic, and the neat thing is just the integration in a comprehensive platform that works. In my time in Mannheim, I was responsible for the SIP pool, so the computer pools for the students, which is nice because then it's easy to ask yourself, may I use them overnight for evaluation? Oh yeah, sure. And so we had the chance to run larger experiments with this platform, then taking the experiments for calibration, putting this in Omnet, and with Omnet scaling the whole thing. And after all, what is research all about? Write papers and PhD thesis. So forget become a good thing. And so we managed actually to graduate a number of very successful and bright young students with the whole thing and did evaluations. So for instance, here we have one thing where we try to understand the effect of errors on our whole thing. So considering a error-free environment, so we have fast nodes and we have a small error rate, and completion time for the evaluation is something below 10, whatever 10 is. Then we were introducing an error rate of 0.25, so a quarter of things just go bad, and also introducing slower nodes in the whole thing. So by using retransmission, this means we are taking surprisingly something like 4 times as long in order to compensate for the whole thing. Now, can we do any better if we are increasing the number of replicas? Yeah, obviously. Same thing like with a fractal or with a Mandelbrot set by overlaying here. You just take another copy once this is done, and obviously you're reducing the error rate by doing the whole thing. So it's just the amount spent, the quality you get. It's pretty much like in internet also, the over-provisioning, something like 4.45, I think, is what you need in over-provisioning in order to guarantee services when you're not able to do reservations. And same thing with the speed filter. Actually, if you then call out the slow ones, then you're actually approaching pretty much, again, the baseline that we had here, which is actually a nice thing. So the take-home message here is, if you have all the money, then actually you can transform an unreliable heterogeneous computing environment into something which looks a bit more homogeneous by the taskers. It becomes a bit more reliable, but at the cost of more replicas of involved resources. And again, the nice thing actually I think is that we had initially, from the beginning actually of the project, a very nice abstraction about how to deliver the whole thing. And this is pretty much the second insight that I might share about how to sell your work. So we're talking about 2010. This interview talk in Bamberg, where we really hadn't had any idea where really to use it and whatever. And edge computing was really starting to rise at that moment. And we discussed and really thought about going for things like IC3 and ICDCS, whatever systems conference, or something like the first, IEEE conference on edge computing and stuff like that. And, it's gambling, always. We did the wrong way, I think, so we didn't go for the edge computing stuff, but we just tried to put it somewhere established, just to have a shiny paper with a hope of citations. And looking at the success of edge computing, well, it's always easier to predict the past than the future, but it might have been the better choice. So it's always about placement and visibility of great research. At least it did get a bit noted, so it's not that lost, but things you wonder if things might have been better. Anyway, we continue the whole stuff, looked at scheduling. So again, it's all about graduating students and finding interesting results in how to manage something which is vastly distributed, heterogeneous, and decentralized. And here, the next thing I just want to briefly touch is about context-aware scheduling. So we are again in edge computing, looking at data that is produced by sensors at different places in the network. So we have effects of locality. We have the assumption that typically when you have sensor data being something visual for inference or you want to process it in a timely manner. And typically we have a distributed edge computing set, so we have smaller devices around which may require services they're not capable of running themselves but need to cooperate with some kind of infrastructure. Be it far away, in the network sense, in the cloud, or something closer, which yield this required timely handling things. Then we have mobile devices by nature come and go. They might be switched off, lying on your desk while you're giving a talk somewhere. They might use services from the infrastructure depending how long they are. And well, the question now is where to place the computation, where to place the data. Is there any dependencies in the whole thing? And a simple observation is if some new data occurs somewhere in the system, and you want to handle it, so after some kind of delay, you're starting thinking about where to place or where to schedule the task. So you are calculating a schedule, then you take the data that has been somehow created by the sensor, you put it where the computation should be, or in our case, you just bundle it as a tasklet, then the computation takes place, then the result is handled, and that's it. Can you improve it? Well, if you know where the data is actually originating and the data is already there where you schedule, or your scheduling takes into account where your data is, then obviously you can have the data transfer problem or the time that you need ahead of the scheduling, and this is pretty much the speed up that you can gain in the whole thing. So question now is how to balance the whole thing and where to transfer and store the data, and in order just to make use of this improvement. And obviously, there are three aspects of the whole thing. We have a three-level scheduler. The first thing considers where to place the data. Simple thing. You flood it, you place it everywhere, then you're free in your scheduling decision and you benefit from everything. Drawback, you have to transfer the data to places which are not interested, which consumes bandwidth. You can have, depending how excessively you do this, you have collisions on your Mac player, you're consuming energy, so it might be simpler to place it only where it's relevant, or just have it at a single source, which pretty much gives the spectrum of choices that you have here. And then also taking some kind of utility function, so place it to devices which are suitable, presumably when later you are thinking about where to place the task. And obviously, your task placement can depend also on things like you can do it kind of randomly. You might consider things like the utility or some kind of a fitness of your device, being the local computing capacity, or kind of a history, whether the device is deemed to be more reliable. So desktop computer might run 24/7, whereas your notebook might be hibernate in between. And these are things which can be easily somehow collected and taken into account of such a function. And you can also consider, is the data that I need already there? So obviously, this would also be a smart part of something like a schedule. And the next thing is you have dynamism. So what happens if things change while you are there and doing things? Sorry. So doing some kind of an adaptation at some point. And how to measure this? This could be keeping track about the number of replicas that you have there, or the load in the system, so something like input queue length. Sorry, these might be effects that you could consider here in this third part of the scheduler. Yeah, I'm showing you this because this is exactly what we did. And so in the first round, what we did was looking at the placement. Obviously, then it might be interesting to see what are the requirements of the application, the fluctuation of the device, the capabilities, and the size of the data, looking at these aspects in the fitness function, and using this just to determine which are good candidates in order to place data. And obviously, the three things, or the variants that you have is you do not replicate at all. So when you need the data, you ship the data where it's needed. And after that, you forget it. If you do the next schedule, you ship it again, which might not be smart, but a viable solution to the whole thing, which might be pretty much the opposite to a full replication. You ship it to pretty much every node in there. one replication means you just have a single copy of the whole thing, and context-aware replication is where we want to go, using this fitness function in order to determine which are good candidates to schedule the whole thing. And then the next thing, when you're looking at the task scheduling, obviously you can do this randomly, so you schedule your task list, which is indicated by this. I always forget it. They Google it, they'll remember it for a month. Hop would be, and there's another. Anyway, this symbol for the gear. Yeah. For the task guide, so here you have the task guide scheduled at a computer where the data isn't. Here you schedule it at a computer with a low capacity or as a mobile device, but at least it has the data. If you're doing this data aware, you at least schedule only where the data is, and obviously in performance aware, you could schedule where the data is, and depending on the capabilities of the local devices. And for the dynamic runtime adaptation, it's just a question between something on the spectrum of no replication and full replication. What is the right degree of numbers of replica in the whole system? And we were just using a rather simple heuristic and taking the input queue length of the running containers. And if you're reducing the number of containers over time, did I mention don't take animated slides from a PhD student before? Anyway, if you are losing replica over time, the input queue length of the remaining taskets will increase, and after you're hitting a threshold, seeing when we're hitting the threshold, you might be happy to start again, and there you are reaching something like a point in time where the systems have to do the whole thing. And we evaluated the whole thing and looked at 3 applications. So the setting was something like having a lab environment where you deploy, which is
yeah, amazing.
You deploy your tasks and your computers and the whole thing. The applications that we had first was something like a face recognition, a machine learning, and a Monte Carlo simulation thing, which showed different characteristics, which would make them nice for us to motivate them, so how to explain and show different characteristics of what is running in the system. And we looked at the different aspects of the size of the tasklet, the speed or the requirements, and the size of the data that is involved, and then looked at the different kind of replication. So if you're doing no replication, 31.61, we have 4 here, so this is somewhere in the Crete sky. So this means for every task that you schedule, you transfer the data. So this is obviously some kind of snippet, and surprisingly it shows. One replication isn't actually that bad when it comes to data transfer, because this is pretty much the bare minimum you have to do. You have to place the data somewhere. And now is the question, what happens if you're doing all the computation on this one replica? Presumably the computation will be higher and taking longer than if you're looking at full or context-aware replication. Actually, surprisingly, even full replication is not that costly in that setting as compared to no replication, which would be, pretty much the most stupid way to handle the whole thing. And then we just took a look at different strategies like random data where performance aware, and actually you can see the penalty clearly when it comes to this one replica, that all the computation is done on this one replica, but otherwise this looks kind of neat, and again, actually under the hood it's all textbook knowledge, so it's nothing somehow evolve the big mechanisms. The neatness is actually the integration of the whole platform and making the things available to a programmer in somewhat nice abstraction. Now that you listen to that, it makes you wonder, why didn't tasklets take over the world? Maybe it was this poor decision trying to get published at some major IEEE conferences at that time, not jumping onto the right kind of fashion at the time. We worked on energy-aware offloading, did a lot of other decentralized scheduling, so it's a neat thing. But to be frank, there are other neat platforms around, and researchers did also other neat things about it. So it's just one among others, to be frank, that is doing the same thing. So I guess most of you are not using tasklets. It's a very rare event if you meet people, at least some know some kind of tasklets, but pretty much everything we are talking about here applies to when it comes to serverless computing and all this decision making. So I guess this is still core to what we talked about when it comes to this edge cloud continuum. So these are the basic things you have to solve in one way or the other way. And I guess there are enough solutions out there. The question is now, why isn't anybody using this? This is the part I cannot answer because this is more marketing question or a technology adoption question. But the last thing I want to mention or just briefly discuss before we go for the group photo, the lunch break, and an announcement by Wolfgang before, is what I think is interesting these days and what we're trying to work on currently in a world after taskless or still with serverless computing in mind, as a question how to use these things or what is kind of nice in there. And the one thing that we did in my group also for some years was configuring automatically distributed applications. And if you're looking at the variety and the changes of devices at the edge, obviously something like a configuration problem makes kind of sense. Then if you're looking at what actually looks like a promising thing, especially if you're looking at the capacity of the local devices, it's hard to find things where you really say you need infrastructure. This is a computer. If you're going 10 years back in time, this was a fantastic computer on your laptop, as a laptop or whatever computer. When people talk about resource constraints devices, this is not a resource constraint device. Your small sensor might be, but you wouldn't deploy anything on a sensor somewhere, maybe some kind of preprocessor. So we're talking, actually, frankly, most of the problems we want to solve are not evident here. Maybe this is one of the reasons nobody is selling you services like that as a telco provider or whatever, because again, these are not resource-constrained devices. These are computers, full-fledged, powerful. So the only chance actually to generate some substantial research questions now is to make the problem harder or anticipate at least something that requires a harder problem. And this is pretty much why not having those AI services which deliver in, remember those 20 milliseconds, this is the time people wouldn't notice to do things, decision making, whatever. And this is what these days are talking about kind of edge AI. So when you combine the stuff which is around, so you might have traffic monitoring cameras around the corner. If you integrate what this camera is doing into your autonomous vehicle, you might reduce the chances to run over a cat or a pedestrian or whatever you consider important in that context. So combining the services, the information that is around there, and trying just to place it to the resources, devices that are available in order to produce timely results. And this in a way that you have something like an add-on security. You would not definitely not offload any crucial decision that is required for your autonomous vehicle to operate at all, but you might utilize add-on functionality which might just simply improve the overall situation in a nice way, just as kind of a motivation there. So the resource question we are trying to understand or solve these days is how to configure an AI application in a distributed way on the devices that you have around there. So for instance, if you have different sized models, small, medium, large, and you have different capacities of the services, you might find different valid configurations. So you could use two medium models or a small and a large model, and you just pick one of the configurations, and you can adapt to other configurations if one of those configurations would break. Now the question is how to determine good mappings or stuff like that of your devices or what you want to have. Like here, for instance, you have some vision capturing by VR glasses, which are resource restricted. You have something like a fog layer of things like clouds and other stuff around in your vicinity, or you can go as a multi-tier thing again on the continuum down to the cloud layer if you have the time for the whole thing, and depending on your application requirement, the task at hand, finding a good mapping of your requirements to the system model. And what we're actually anticipating or want to come up with, and it's really a research question, but I hope I can end with that and deliver some enthusiasm about what's it all about. The question is, if you're looking at those placement problems, typically what people did is using some ILP, constraint section programming, whatever stuff, just to say, I have these components, I want them to be running up fulfilled, so I have to find a mapping to the available infrastructure. So a classical optimization problem with some kind of constraints for the placement. And now, well, kind of a shame that I'm starting to talk about this. The cool thing would be, at which point in time do you get a benefit if you just remember things, learn things? So in the mornings, you don't go into your kitchen, sort all your cupboards in a new optimized way, and then pick your mug. No, you open the right closet, take your mug, pour your coffee, and you're a happy camper, right? So at some point of stability in time, obviously, a trained, a learned configuration might be beneficial if you don't have to run this optimization and placement thing all the time, right? So trying to understand how learning and this classical optimization placement, how they could play together, at which point it might be beneficial to retrain or relearn and see whether you can get better at the configurations, or whether it's safe just to see whether something you have learned will apply. So you need to have something like stability metrics, seeing what has changed over time, something like devices, services that are available there. If things are added, then obviously everything that you did before might apply as well. Only if you're losing things, then you might run into something where you might have to do another optimization run. But if you add things, then you might miss out a better configuration. So from time to time, it would make sense just to jump in and do something like an optimization. And the research question actually here is then trying to answer when is learning better with respect to stability than optimization, and then finding also an architecture in which this will work. So how to link your optimization and your learning problem. And our approach will be using graph neural networks, which we will then use as configurations as an output from the constraint-based optimization, feed this into the learning model. Well, and this is pretty much where we are right now. So we're starting to model, to code, and hopefully coming up next year with some interesting resource where I can tell you, well, if your stability metric is 0.74 or whatever, I have no idea yet, this will make sense. It might turn out that actually learning might outperform all the optimization stuff, or the other way around. It doesn't make any sense. We simply don't know, but I think this is a nice question and worth giving an answer to this. And this is what we're pretty much doing. So coming up with the necessary application models, this is where we want to use the graph neural networks. We need also middleware services, because we're notorious about building middleware services. And if you haven't done it, making middleware systems is cool. Anyway, in order just to discover, finding things, monitoring the whole stuff, creating scenarios, and then by these scenarios seeing how the different configuration things will apply and compare, and then coming up with something like an adaptive thing. And with that, I finally managed to bring us close to the photo session. I hope I could convince you that, well, some part is old hat. Edge computing, pretty much all of us know, but that there's still interesting thing to do in edge computing, even though it's not necessarily something you might directly book a service at your telco provider, but I guess from an academic perspective, it's still intriguing, and there are a lot of things where we really might utilize resources that are already at hand, instead of building new compute centers, talking about new renewables or nuclear power or whatever, in order to just create more cat videos or whatever people do with AI. I guess right now, becoming frugal is actually one of the things we can do. Just utilize what we have, coming up with good schedules, and maybe this is one way to make the world a bit better besides drinking red wine, or we decided not to do the karate thing again, right? So again, I hope this will foster some discussions. I'm around here the next day, so feel free to approach me whenever break, or just start hitting now. Thank you.
Thanks for your talk. I do not really have a question, more small comment. Yes, you particularly mentioned that a smartphone is not a resource-restricted device, but I'm a little bit surprised about this. I don't want to fight about terminology, but if you look at the smartphone, you have a small screen, you have no keyboard.
Right. From an HCI perspective, you're absolutely right, but this is above my pay grade. I'm just a systems person. Melanie is doing the HCI stuff in my group. Yeah, it's the usability is a complete different thing. Right. Why not?
So,
I lost the edge.
thank you for the talk. Especially thank you for the animations, they were really nice.
That was Martin now, mainly.
So it seems in your world you assume trust of all the components. So they expose what they can do and they're honest. And you can offload and you're sure that they're going to do it. But what if you cannot make that assumption? Does it change a lot in your model and your vision?
Hand waving. Frankly, it's the old delicious host problem over and over again. Either you're going to something like either having trusted computing environments, or you're operating in something like a chain of trust with certification authorities, and you have certificates, but you need something in order to trust. I definitely wouldn't hope that the world will become good after all and doing the whole thing. So, but we
Depends how open your world is, basically.
yeah, we completely ignored it so far, but some kind of mechanism for that will be necessary, absolutely.
A similar question. You assume all the devices you use in the complete continuum are only used for your optimal, for your job, right? You send at the beginning, you send this thing and you get a turtle or a Ferrari to make it a high-level device, and then someone starts using his device and it gets a turtle for your device. What do you do about that?
Well, it's the classical Boeing problem that the people in grid computing had. Yeah, you need to adapt the fitness functions. We had also some scheduling which would work on varying loads and accommodate that. But actually, over-provision is the only answer you can have in order to add elasticity in that sense.
And you could have feedback in between,
Yeah.
right? Okay, thank you.
Otherwise, it would work.
Frank, you have a question? No. Okay, then thank you. Wolfgang has a question. No, he has an announcement.
I have neither a question nor an announcement,
Good.
but just a remark, if you allow me to do that. First of all, I like this talk a lot. So you started with the question, what is missing in between cloud computing and mobile edge? And there is something missing. I think we all agree on that, but you'll be surprised what my suggestion would be. What is missing?
Internet?
No. No, not yet. Let me say not yet.
Not yet.
What is missing there is a fundamental theory of informatics. Because classical, so-called theoretical informatics started it was fine in the 1960s. With the computer, with one computer, you computed one function. You are only interested in terminating runs. So that was fine. But nowadays, the world is completely different, and we don't have any fundamental concepts to cope with this world. And the term theoretical computer science that was coined about 60 years ago, nowadays is no more in any sense adequate. And we need a more fundamental notion of what we have here. And what we have is a kind of, I hope you agree with this, is a kind of modules or components, call them however you wish, and how to compose them. And this must be simple and easily doable once and for all, and then you can start with specialities.
I totally agree. There's nothing more practical than a good theory, and this has to be something that is understood and has to do with the programming model. And without this is just some kind of crafting. Yeah, you're absolutely
But why don't you do this instead of?
Well, to some degree, actually, part of what we are doing is, if you're looking at ILP or CSP as a solution to the whole thing, is just mapping this to well-understood problems that you can find and match there. We had a discussion actually, and I was part of the collaborative Research Center Marki at Darmstadt. And Alex Buchmann also started talking about why don't we have a theory about transition, so about adaptation and things which happen over time. Now we're coming back to Petri nets, saying from which states can I reach another state is safe, and obviously there are different paths which are possible. And a lot of what we are doing, even if we're doing it at design time is completely lost when it hits runtime, where actually it should be there in order just to monitor and see whether your application is conforming to the specification, if there was one in the first place, that somebody actually created for that. Yeah.
Okay, so I think we agree, but one additional remark why I didn't immediately say yes, Petri nets is that the notion of components and composition is so far not in a satisfactory way covered, has not been covered by Petri nets nowadays, and this should be considered more carefully.
Well, it starts, actually, if you're looking at starting from Maillet's contract-based programming and stuff like that. But again, this still has the notion of single threads of control, which run sequentially through one program. There's no notion of asynchronous behavior, parallelism, side effects that can happen. So if you want to add this and add all the Lampert specification stuff, I guess we're not yet there.
Add this in a much more systematic way and make it a scientific theory. So what informatics offers so far, that is not science, that's just playing around a little bit. So the distance between the
At some point I have to disagree.
Okay. I said, tell you why I think I make this, I know it's a provocative remark. So in a good science, you have a quite abstract theory. For physics, for instance, the distance between the theoretical concepts and the world it is described by the theoretical concepts. That is a real distance. In informatics, it's laughable.
To me, part of what we're doing is engineering. I shouldn't say it loud, but
Okay.
there's nothing wrong with engineering if you're creating products, right?
Good answer, I agree.
That's a very, very good point, Wolfgang.
Okay. So the next, Frank, you have a question? No. Okay, so the announcement is that we have a group picture right now, outside, I guess, right? Yeah.
Wolltest du noch was sagen?
And then we start back at 3 o'clock. Okay?
Ja. Also, also ich glaube, beim nächsten Leben, wenn ich nochmal zurückdrehen würde, würde ich wahrscheinlich viel früher mit Online-Model-Checking anfangen und mir darüber Gedanken machen, statt irgendwie Dinge zu coden.
Bevor du dich hier zu sehr einlässt.
Auf die falsche Seite kommst.
Wolltest du noch kämpfen?
Ja. Wir machen das.
Sachen kann man nicht hier lassen, ne? Sag mal.
Of course, this year
Der bei der Massenausbildung hier Richtung Bezüchtung dort hat ja, ich weiß nicht.
Ja.